The first person who will live to 150 may already be alive, or no human may ever reach it. Both statements are scientifically possible, which is a slightly inconvenient result after centuries of searching for a clean answer. We know a mouse can live about 4 years. A dog may reach its 20s. A bowhead whale can survive beyond 2 centuries. Humans, meanwhile, have built intensive care units, transplanted hearts, sequenced genomes, and invented a watch that reminds us to stand up. Yet our verified record is still 122 years. It has not moved since 1997. So is 122 a coincidence? Is 125 the wall? Could an extraordinarily lucky person reach 150? Or does human lifespan have no fixed maximum at all? The answer depends on what possible means. Possible with the body humans have now? Possible with perfect healthcare? Or possible after medicine begins changing the biological machinery of aging itself? Those are 3 different questions, and people regularly pour them into one headline, stir vigorously, and serve confusion. We should begin with the one number that is not theoretical. Jeanne Calment was born in Arles, France, in 1875. When she entered the world, electric lighting was still a novelty, the telephone was barely a device, and nobody had yet looked at an airplane meal and felt disappointed. She died in 1997, at 122 years and 164 days old. Her age was supported by birth records and multiple censuses. Others have claimed to be older, but extraordinary birthdays require extraordinary paperwork. Unfortunately, probably very old is not a scientific measurement. Calment remains the longest fully authenticated human life. The second-place record is under 120. That gap is strange. World records normally fall as populations grow and conditions improve. More people now survive childhood, avoid infection, control blood pressure, receive surgery, and live into old age. The world contains far more potential supercentenarians than it did a century ago. Yet no verified person has reached Calment. She has been sitting at the edge of human life for almost 3 decades, apparently refusing to move despite being dead. This looks like a limit. But a record is not the same as a limit. Imagine rolling dice and recording the highest result. Human survival, unfortunately, is not a neat 6-sided object. Few people reach extreme ages, medical conditions change across generations, and chance becomes enormous. A maximum observed lifespan tells us what happened. A maximum possible lifespan tells us what cannot happen. Those are separated by an uncomfortable amount of mathematics. Life expectancy causes even more confusion. It is the average number of years a person is expected to live under a given set of mortality conditions. Maximum lifespan is the farthest edge reached by an exceptional individual. Improving life expectancy does not automatically push that edge outward. If a society prevents infant deaths, treats infections, reduces smoking, and controls cardiovascular disease, millions more people may reach 80 or 90. Average lifespan rises dramatically, but the oldest person might still die around 115 or 120 because a different set of failures dominates at that age. Public health removes early traps, vaccines, sanitation, antibiotics, surgery, and safer childbirth let far more travelers move down the road. But eventually they reach a bridge that is slowly collapsing. Saving people from earlier traps does not repair the bridge. It creates a larger crowd standing on it. The bridge is aging. For much of adulthood, human mortality roughly follows the Gompertz pattern. The risk of death rises exponentially with age. It does not increase by the same amount each year. It multiplies, historically doubling roughly every 8 years in many populations, though the exact pattern varies. That sounds abstract until you imagine a machine whose chance of failing doubles again and again. At 30, most parts recover well. At 80, several systems have lost reserve capacity. At 100, even highly selected survivors have little room for another infection, fall, blood clot, or bad Tuesday. Then something surprising may happen. At the most extreme ages, the rise in mortality appears to slow. A major study of Italians aged 105 and older found that death rates reached a plateau. Beyond 105, each additional birthday did not seem to make the annual hazard climb as rapidly as the classic curve predicted. This does not mean the oldest people stop aging. It means their risk may become brutally high and then remain brutally high. Think of a coin toss every year in which one side says next birthday and the other does not. Even if the probability stops worsening, surviving many consecutive tosses becomes extremely unlikely. If an individual has roughly a 50-50 chance of surviving each year after 105, reaching 115 requires winning around 10 times. Reaching 125 requires around 20. The exact odds are debated, and real mortality is more complicated. But the principle is simple. No wall is required. Probability can behave like one. This is why some demographers argue there is no fixed age at which humans must die. If mortality plateaus below certainty, then a person could, in theory, continue surviving year after year. There would be no birthday when biology receives a notification saying, "Account expired." But no fixed wall does not mean unlimited life. A fair coin could land heads 100 times in a row. Nothing in the rules forbids it. You should still avoid building your retirement plan around this event. Population size matters. If only a few people reach 110, even a survivable risk will rarely produce someone aged 125. If billions eventually reach 110, records should move because humanity is buying more lottery tickets. The biological argument is less cheerful. Your body is not one object aging at one speed. It is a federation of organs, tissues, cells, microbes, repair systems, and signaling networks that gradually become worse at keeping one another stable. Scientists describe several interacting hallmarks of aging. DNA accumulates mutations and other damage. Telomeres, protective structures at chromosome ends, shorten in many dividing cells. Epigenetic patterns that help cells control which genes are active become altered. Proteins are damaged, misfolded, or cleared less effectively. Mitochondria become dysfunctional. Nutrient-sensing pathways drift. Stem cells lose capacity. Senescent cells accumulate. Communication between tissues changes. Chronic inflammation rises. Autophagy, the cell's recycling and cleanup process, becomes impaired. Even the relationship between the body and its microbes can deteriorate. This is not a list of 12 independent villains waiting politely for separate movie contracts. They interact. DNA damage can produce dysfunctional cells. Dysfunctional mitochondria can increase stress. Senescent cells release inflammatory signals. Inflammation alters tissue environments. Stem cells then struggle to repair those tissues. Damaged proteins accumulate because cleanup systems weaken, which creates more cellular stress. The body begins losing the ability to return to normal after disruption. This ability is called resilience. A younger person may develop an infection, spend several miserable days becoming personally acquainted with every blanket in the house, and then return near baseline. An older person may survive the same infection but never fully recover previous strength, balance, appetite, or cognition. Each shock takes something. Eventually, the body cannot rebuild the distance between ordinary function and catastrophe. One study examined repeated blood measurements and physical activity patterns across age. The researchers found signs that recovery from disturbances became progressively slower. Extrapolating those trends suggested complete loss of physiological resilience somewhere around 120 to 150 years. This is the origin of the famous 150-year human limit. It is not evidence that someone lived to 150. It is not a timer discovered inside the liver. It is an extrapolation from biomarkers measured at younger ages projected toward a theoretical point where recovery time becomes effectively infinite. The study is valuable because it treats aging as loss of stability rather than one disease. But the range is wide, and extrapolating beyond the ages well represented in data is always dangerous. If you measure a staircase for 10 steps, you may predict where step 20 will be. You should still check whether the staircase continues. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. Another analysis has produced an estimate around 138 years. Other demographic work placed the practical ceiling near 125. Forecasting studies suggest the 122-year record is likely to be broken this century and assign some probability to a person reaching the high 120s or beyond. These estimates disagree because they use different assumptions about mortality, future medicine, population size, and record quality. At the edge of a distribution, changing one assumption can move the answer by years. There is also a cruel selection effect. People who reach 105 are not ordinary people who simply kept going. They are survivors filtered by genetics, development, behavior, environment, wealth, healthcare, chance, and the deaths of everyone more vulnerable. This can make late-life mortality appear to slow. Frailer individuals die earlier, leaving a population increasingly concentrated with unusually robust survivors. The remaining group may show a flatter mortality curve even while every individual deteriorates. Statistics can look optimistic for a deeply pessimistic reason. So why does the human machine age at all? It is tempting to imagine aging as an intentional program, as if evolution installed self-destruct software to prevent grandparents from occupying too many seats. Evolution is less organized. Natural selection strongly favors traits that help organisms survive to reproduce and support offspring. Its force generally weakens at later ages. A genetic effect that improves early reproduction but causes damage decades later may still spread. Maintenance systems only need to be good enough under ancestral conditions where infection, injury, hunger, violence, and childbirth often killed people before extreme old age. Perfect repair would also be expensive. Energy spent maintaining every molecule forever is energy not spent. Growing, reproducing, escaping danger, or feeding children. Organisms evolved compromises between repair and reproduction, regeneration and cancer prevention, immediate survival, and long-term durability. Telomeres reveal this compromise. Each time many human cells divide, their telomeres tend to shorten. When telomeres become critically short, cells may stop dividing or malfunction. This helps limit uncontrolled proliferation, which protects against cancer. So why not activate telomerase, the enzyme that rebuilds telomeres, everywhere? Because cancer cells frequently exploit telomere maintenance mechanisms to keep dividing. Giving every cell a permanent license to replicate could repair tissues beautifully right up until a tumor sends a thank you card. Longer telomeres are not an immortality setting. They are part of a trade-off. Cellular senescence creates another. A damaged cell may enter a state in which it stops dividing. Early in life, this can suppress tumors and assist wound healing. Later, senescent cells accumulate and release signals that promote inflammation and tissue dysfunction. The same defense that prevents one disaster can slowly contribute to another. Aging is filled with this kind of biological paperwork. Cancer matters because surviving longer gives mutations more time to occur and damaged clones more time to expand. But preventing every cancer would not grant centuries. Heart disease, stroke, dementia, kidney failure, lung disease, immune decline, frailty, infections, and failures we have not named would remain. Eliminating one disease adds fewer years than people expect because other causes take over. If a 95-year-old is saved from a heart attack while every other system remains 95, the body does not become 40. It becomes a 95-year-old without that heart attack. This distinction separates disease treatment from age modification. Modern medicine is excellent at replacing particular failures. A cloudy lens receives a new one. A blocked artery is opened. A damaged hip is replaced. A bacterial infection is attacked. A failing organ may be supported or transplanted. These victories extend lives. But eventually, the patient contains too many interacting vulnerabilities for one repair to restore the whole system. It is possible to replace a heart. Replacing the blood vessels, immune system, connective tissue, kidneys, nervous system, bone marrow, and every mutated cell at once is a less convenient appointment. The brain creates the hardest boundary. Many body parts can theoretically be replaced while preserving the person. Replace enough of the brain, however, and the question changes from did the patient survive to who exactly came home? Neurons can live for a lifetime, but that lifetime exposes them to protein aggregates, vascular damage, inflammation, metabolic stress, and loss of connections. Preventing dementia is therefore not merely another maintenance task. It is central to making extra years belong to the same conscious individual. A body surviving for 150 years while the mind disappears at 90 is not the victory people mean when they ask for longevity. They mean health span. Health span is the period lived in reasonably good health. Lifespan is simply the time before death. Extending the second without the first could create decades of frailty, dependency, pain, and cognitive loss. The true goal is not to keep the final breath permanently postponed while everything preceding it collapses. It is to delay the collapse. Some rare people already demonstrate compression of morbidity. They avoid major disability until unusually late, then decline over a shorter period. Supercentenarians may possess protective combinations of genes and physiology, but there is no single longevity gene that explains them. Variants near genes such as FOXO3 are associated with exceptional longevity. Yet, genes are not destiny, and genetics explains only part of lifespan variation. Jeanne Calment did not carry one magical switch labeled 122. She carried a combination no one can fully reconstruct, avoided countless lethal events, received care, and benefited from chance so extreme that billions failed to repeat it. This is why longevity advice from one record holder is entertaining but weak science. Some centenarians credit olive oil. Others credit faith, chocolate, avoiding men, enjoying men, drinking alcohol, refusing alcohol, or simply not dying. When millions follow different habits and only the longest survivors are interviewed, the advice becomes highly selected. Healthy behavior still matters. Not smoking, exercising, sleeping adequately, eating well, controlling blood pressure, receiving vaccines, and using preventive care improve the chance of reaching older age in better condition. But these actions improve your odds within the current game. They do not prove the game has no final level. What about calorie restriction, supplements, fasting, young blood, cold exposure, metformin, rapamycin, or the mysterious powder currently being promoted beside a shirtless 70-year-old? Some interventions alter lifespan or health span in animals. Calorie restriction can extend life in several species under certain conditions. Rapamycin extends lifespan in mice. Senolytic drugs aim to remove senescent cells. Researchers are studying partial cellular reprogramming, gene therapies, immune rejuvenation, stem cell restoration, and ways to repair molecular damage. This is real science. It is not yet proof that a healthy human can live to 150. Mice are useful because experiments finish within years. A human lifespan trial may outlast the researcher's career, the funder's patience, and several generations of fashionable terminology. Biomarkers can speed testing, but they introduce another risk. A treatment may make an aging clock report a younger number without producing meaningful health or longer survival. Improving the dashboard is helpful only if the engine agrees. No approved intervention has been shown to reverse whole-body human aging enough to push maximum lifespan far beyond the verified record. And ordinary supplements should not be confused with experimental rejuvenation. If a capsule genuinely added 50 healthy years, its manufacturer would probably lead with clinical survival data rather than a photograph of blueberries. Still, animals prove that lifespan is biologically adjustable. Species age at radically different rates. A mouse and a bowhead whale use similar molecular ingredients, yet one may live a few years and the other more than 200. Some organisms even show negligible senescence under particular conditions. Nature has not discovered one universal expiration date for living tissue. It has evolved different maintenance strategies. That means the present human limit is not necessarily a law of physics. It may be an engineering property of Homo sapiens as currently built. Engineering properties can sometimes be changed, but changing them safely is harder than copying one long-lived animal. Bowhead whales evolved their metabolism, DNA repair, cancer defenses, and life history together. Borrowing one gene would not turn a cow human into a compact land whale with excellent insurance. Long life requires coordinated systems. This brings us back to the three versions of possible. Under present biology and present medicine, 122 is the verified record. A person reaching 125 or perhaps 130 is statistically plausible, especially as more people survive past 100. It would be extraordinary but would not require rewriting biology. Reaching 150 under the same conditions is far more doubtful. One resilience model places an absolute boundary somewhere between 120 and 150, but that range is an extrapolation, not a reservation. Demographic probabilities become microscopic. Every organ must avoid catastrophic failure for decades beyond ages at which almost all humans have died. The body would need to win year after year while carrying damage from every previous round. It is possible in the narrow mathematical sense that no specific birthday forces death. It is not supported as a realistic outcome for an unmodified human. Now, treat today's major diseases but leave aging untouched. More people reach extreme age and records may move. But loss of resilience, frailty, immune dysfunction, and multi-organ decline eventually dominate. Radical extension remains implausible unless aging itself is markedly slowed. Finally, allow medicine to alter aging. Now the question has no responsible numerical answer. If therapies can repeatedly remove senescent cells, restore stem cell function, repair mutations, reset harmful epigenetic changes, maintain proteins, rejuvenate immunity, preserve the brain, prevent cancer, and restore resilience without causing new disasters, then 150 may stop being a limit. But that sentence contains nearly the entire field of biomedicine pretending to be a treatment plan. Solving one hallmark may help. Solving all of them in a living human, repeatedly, safely, affordably, and without erasing identity, is another scale of problem. Some futurists describe longevity, escape velocity. Medicine adds more than 1 year of remaining life during each year a person survives. If that happens, individuals could remain ahead of age-related decline as treatments improve. The concept is logically possible. It is not a timetable. Nobody knows whether the first decisive therapies are 10 years away, a century away, or blocked by complexities we have not yet understood. Aging research has advanced rapidly, but biology has a habit of hiding extra machinery behind every mechanism we confidently announce. There may also be new limits beyond aging. Even a perfectly maintained person faces accidents, violence, novel infections, environmental disasters, and statistical bad luck. An ageless human would not be invulnerable. If annual risk never reaches zero, survival still declines across centuries. Immortality is not merely extreme longevity. It is the elimination of every possible cause of death. That is not on the clinical trial schedule. So what is the maximum possible human lifespan? The honest answer has layers. The maximum demonstrated lifespan is 122 years and 164 days. The maximum likely lifespan for humans living with current biology appears to sit somewhere not far beyond that record, often estimated around 125, with higher values such as 130 or 138 possible but increasingly rare and uncertain. A frequently cited biological model gives an outer range of roughly 120 to 150 years based on total loss of resilience. It does not establish 150 as an achievable natural lifespan. Without interventions that slow or reverse aging itself, a healthy 150-year-old remains speculation. With such interventions, the ceiling is unknown because the organism being measured would no longer be aging in the ordinary human way. That last distinction matters. Asking how long an untreated human can live is like asking how far the first airplanes could fly. The answer describes a machine under particular constraints. It does not reveal how far every future machine must fly, but we should not confuse the existence of future engineering with proof that it will arrive. For now, humanity has one authenticated person beyond 120. 1. She crossed a boundary that billions did not, and nobody has followed her through it. That does not prove a solid wall stands at 123. It reveals something almost as intimidating. Beyond 115, probability, accumulated damage, and loss of resilience combine into a region where survival becomes extraordinarily difficult. The wall may not be made of stone. It may be made of 1,000 small failures. A stem cell that no longer divides correctly. A protein the cell fails to clear. An immune response that arrives too slowly. A blood vessel that has endured 1 decade too many. A brain that cannot fully recover from the next disruption. No single failure defines the maximum. The maximum emerges when repair loses its race against damage across the entire body. That race is why 122 remains both a record and a warning. Human life has already been extended enormously by removing early causes of death. The next great increase will not come from one more cure added to the list. It will require preserving the system that survives those diseases. Maybe the first 150-year-old is alive. If so, that person probably will not reach 150 because of one perfect diet, one fortunate gene, or heroic commitment to expensive powder. They will reach it because medicine learns how to make an old body recover like a younger one, then does it again before the recovery itself fails. Until that happens, the best scientific answer is less dramatic than immortality and more fascinating than a fixed deadline. Humans do not appear to have a precise expiration date. We have an increasingly narrow corridor of survival. Jeanne Calment traveled farther through it than anyone we can verify. At 122, the corridor has not been proven to end. It has simply become so narrow that, for nearly 30 years, nobody else has made it through.